Hey, welcome to my video editorial for Codeforces round 979. There are going to be hints and I'll explain my thought process behind all the solutions and the intuition behind them, so hopefully you'll have a better idea on how to solve the problem and solve future problems. When I give a hint, don't be afraid to pause and think more about a problem, and I hope you enjoy and learn something. Problem A. In this problem, we are given an array of integers and we can shuffle them around however we want to. The score of this array is the sum of prefix minimums minus the sum of prefix maximums. We want to find the max possible score after shuffling the array. Firstly, what's the largest possible score for one index? Claim the largest possible difference is the max element minus the min element. Now how fast can we achieve this difference? We can achieve this in the first two elements. Just put the max element in the first index and the min element in the second index. This way the score is the max element minus the min element times n minus 1. We multiply by n minus 1 because this maximum score occurs at all the indices except the first one. For the index, the first score is always 0. The code is straightforward. We will sort the array and print the last element minus the first times n minus 1. Problem B. In this problem we have a binary string. The oneness value of the string is equal to the absolute value of the number of subsequences that contain the number 1 minus the number of subsequences that do not contain 1. Let's look at this binary string. It has 7 subsequences and 6 of them contain a 1, while 1 does not, so the oneness of the string is 6 minus 1 equals 5. Something to think about is how many subsequences exist with a size of n. Let's look at the first character of the string. We can either choose to include it or exclude it, so we have two possible choices. And for the second element, we can also choose to include it or exclude it, and we have the same choice for the third element. So for each index, we can include it or exclude it. So there are 2 times 2 times 2 equals 8 possible choices. But wait, if we exclude all of them, we get an empty string, which we don't want, so we subtract 1. So that's 8 minus 1 equals 7 possible subsets. What if the size of the string wasn't 3? We would have n choices, so we would have 2 to the n minus 1 possible subsets. What's the lowest number the oneness can be? It's impossible for it to be 0 because you can't divide an odd number into 2 even numbers. However, a oneness of 1 is possible. How can we accomplish this? If we want a oneness of 1, we need to have 2 to the n over 2 subsequences that have a 1, and 2 to the n over 2 minus 1 that don't have a 1. How can we do this? We claim that a string with a 1, 1 has a oneness of 1. Let's look at this string on the screen. There's a 1, 1, and 4 zeros. What is the oneness of the string? There are 2 to the 4 subsequences with 1, because we have to include the index with 1, and we can choose to have or not have any of the zeros. And there are 2 to the 4 minus 1 subsequences without a 1. This is because we can't choose an index with a 1, and we can or cannot have any of the indices with a 0, but we can't have an empty subset. So that's 2 to the 4 minus 2 to the 4 minus 1, which is equal to 1, so we achieve the oneness of 1. And the code here is really simple. We just print 1, 1, then n minus 1 zeros. Problem C. In this problem, Alice and Bob are playing a game where they have a binary string. In this binary string, 1 is true and 0 is false. Each turn they can place and or between the booleans. After each space is filled, this is how we evaluate the statement. First, we will evaluate all the operators with and. Following that, we will evaluate all the OR operators. In this example, we will evaluate the second and third elements where we get false. Then we evaluate that element with the last element, where false and false equals false. Finally, we evaluate the OR. True or false evaluates to true. This means the entire statement evaluates to true. Alice's goal is to have the final statement be true, while Bob's goal is to have it be false. Our goal is to find what the final statement will be if both players play optimally. When we're thinking about this task, it's a good idea to look at the truth table. If two values are true and true, No matter if we put or and next to them, it will always be true. Now let's look at a true next to a false. This will only evaluate to true if there's an or between them. This means if there's an or next to a true after all the and operations, the statement will be true. When will this be true? There are two possible cases where this is true. First is if the first element is true. In this case, Alice places an or next to the first element. Bob cannot do anything to turn the first true into a false, so Alice wins. We can use similar logic to find that this is true if the last element is true. How else can Alice win? Let's look at what happens when there are two adjacent ones. Bob can place an and between the two trues, or between the true and the false. If Bob places the and between the two trues, Alice can place an or after the second true to win. Otherwise, if Bob places the and after the two trues, Alice can place the or in the middle to make sure there's an or next to a true to win. The code here is very simple. All we have to do is check if the first element or the last element is a 1, or there are two consecutive ones. This can be done with a simple for loop and if statements. Problem D. Here we are given a permutation of length n. A permutation of size n has every character from 1 through n occur once in it. Also, we're given a string of length n. Each character in the string is L or R. L means we can swap that element with the element at the previous index, and if it's R, we can swap it with the next index. We are also given some queries. In each query, we can change the value of the string at a certain index. If it is L, we turn it into R. If it's R, we turn it into L. After each query, is it possible to sort the array? First, we should look at how we are restricted. Let's draw the possible swaps. Here, we see when an L is next to an R, we cannot swap the elements between them. How can we check if this block is stopping us from sorting the array? Let's say we're blocked from swapping elements I and I plus 1. If there's an element greater than I at an index less than or equal to I, we can't get it to its position because we're blocked from doing so. How can we find if a block prevents us from sorting the array? Let's look at the prefix max array. If the prefix max is larger than I, this means there's an element greater than I that is being blocked. Let's update index 2. The previous blocked position is now open, and now we can sort the entire array. Every time we update the array, we can get a blocked or break a previous block. If we get blocked again, we can increase the number of positions that block us. If a position that previously blocked us is now clear, we can decrease the number of positions that block us. If a position that previously blocked us is now clear, we can decrease the number of positions that block us. It is possible to sort the permutation if there are no positions that block us. Let's code this up. It's more implementation heavy than previous problems. First, we input everything. Let's look at the check function. In the check function, we look at an element and the next element and see if it's blocked. We have a boolean called add. If add is true, that pair exists in the array, and we add it to the block count if it's blocked. If add is false, we're removing that pair from the array, and we subtract in this case. First, we check the string in its original state and see how many blocked indices exist. Then we move on to the queries. Changing a position can only affect that index and the index before it. Firstly, before changing, we see if those indices are already blocked, and then we update it and check if there are any new blocked elements. The answer is yes if there are no blocked elements, and no if there are more than 0. Problem E. First, this problem deals with a mex. What is a mex? Mex is the minimum whole number not in the array. For example, for a multiset of 0, 1, 1, 4, 5, the mex would be 2 because 0 and 1 appear but 2 does not. For this problem, we define the score of an array. We take an array and we partition it into any group of multisets we want. The score of the array is the sum of the mex of each multiset. Let's look at the array on the screen, 0, 0, 0, 1, 1, 2. Here I color-coded the multisets. The mex of the green subset is 3, the mex of the blue subset is 2, and the mex of the red subset is 1. so the score of array B is 1 plus 2 plus 3 equals 6. In this problem, we are given an array A, and our goal is to find the score over all subsets of A. Firstly, let's try to solve this subproblem. Given an array B, find the score of it. Obviously, we should put all the zeros in a different multiset. Each zero will increase the score by 1. For the ones, we should also put them in different multisets so they all increase the score. However, they have to be in a multiset with 0. However, there are 4 ones and 3 zeros, so only 3 can increase the score. The fourth one won't help us in any way. For the 2, we can put it in a multiset with a 1 and 0 to increase the score, but what about 4? For 4 to increase the score, it has to be in a multiset with 3, 2, 1, and 0. However, there are no 3's in the array, so the 4 can't increase the score of a multiset. Do you see a strategy here? We can go from small to large. If the number is 0, we create a new multiset. Otherwise, we can try to add it to a multiset to increase the total mex. With this, we can notice the nth occurrence of a value x will increase the mex only if there were at least n occurrences of the previous values. Let's try to use the contribution technique on the problem. This is useful in many combinatorial problems. We'll try to look at each element and see how many subsets this element increases the score in. Let's look at the array 0, 0, 1, 2, 2. First, let's try to compute the contribution of the zeros. How many ways are there for us to choose at least one zero? There are 2 squared ways to choose a subset of zeros. However, one of them is an empty set, so there are 3 ways to choose a subset of zeros. What about numbers greater than 0? We currently do not care about these numbers, as we can have them or not have them, and it doesn't affect our result. Therefore, there are 2 to the k ways of choosing these elements, where k is the number of elements larger than 0, because we can include them or exclude them. In this example, there are 3 times 2 cubed, which equals 24 subsets, where at least 1 0 increases the score of the subset. How many subsets are there that have at least 2 zeros that increase the score of the subset? Firstly, how many ways can we choose the zeros such that there are at least 2? The number of sets of at least size 2 equals the number of sets of at least size 1 minus the number of sets of size 1. How many sets of zeros are there of size 1? There are 2 choose 1, which equals 2 of these. So there are 3 minus 2 equals 1 ways to select a set of zeros that have at least 2 zeros. How can we generalize this? Given n zeros and k elements greater than 0, what is the contribution of zeros to the score? Let's define ways ij as the number of ways to select a subset of all the values of I of size at least j. In ways ij is equal to 2 to the n minus the sum of n choose nk for all k between 0 and j minus 1, and n is the number of times I appears in the array. What about numbers greater than 0? For 0, we did not need any previous numbers, but for greater numbers, we need at least n of each previous number. Let's go back to our example from earlier. For 1, there is only 1 way to choose a subset of at least 1. However, there are 3 ways to choose a subset that has at least 1 0. So there are 1 times 3 ways to have 1 increase the score of a set. Let's define ways where total ways ij is equal to the number of ways to have the jth occurrence of a number I contribute to the mex. We previously found how many ways to have a set with at least I occurrences out of n numbers, so total ways ij will just be equal to that times the ways to have at least n occurrences of all the numbers from 0 to I minus 1. So for I is greater than 0, total ways ij would equal total ways I minus 1j times the ways ij. Once we have the total ways, we can multiply it by 2 to the k, where k is the number of values greater than I. Let's look at the code. Here's the combinatorics template I use to calculate powers of 2 and n choose r. I will not be explaining it here, but I will link some tutorials on combinatorics to learn about it. First, we will input the array and take note of the occurrences of each value. Then we will calculate the number of elements larger than I for all values of I. Then we properly resize the ways and total ways vectors. For the jth occurrence of I to count towards the contribution, all values before I must occur j times. To make sure this stays valid for all values of j and I, we can resize these vectors to the prefix min. Finally, we can start computing the answer. Now we calculate ways and total ways as were mentioned previously. Take careful account of the modulo in the problem. If any number becomes negative, we need to correct that by adding mod to make it positive again. Finally, we can add to the answer the total ways times the number of ways to select larger elements, and we have our answer. Problem F. In this problem, let's say we have an array B. Let S be the set of all distinct integers in B. In one operation, we can select an element V from S and delete a subarray that only contains V, then delete V from S. Is it possible to make B empty? Let's look at the array B equals 2, 1, 1, 3, 3, 1, 1, 2. S would be equal to 1, 2, 3. First, we can select 3 and delete the middle two 3's. Then the array becomes 2, 1, 1, 1, 1, 2. Then we can select 1 and make the array 2, 2. Finally, we can select 2 and make the array empty. In this problem, we are given an array A of size n in Q range queries. For each range query, we have to answer, can we empty the subarray LR? Hint 1. When can we not empty the array? Try to draw some impossible cases. What do you notice? Take this case, for example, 1, 2, 1, 2. Every operation has to erase all occurrences of V in the array, because we can only do each operation once per value V. This means when we do an operation with the value V, all occurrences of V have to form a subarray. Here there are no elements that form a subarray, so we can never erase the entire array. Let's try to generalize this. For 4 indices I, j, k, t, if AI equals AK and AJ equals AT and AI does not equal AJ, it's impossible to empty the array. Why? Because we can't do the operation with value AJ before doing the operation with value AI, and we can't do the operation on value AI before doing the operation on value AJ, therefore we are stuck. Can we find the smallest value of t given a fixed I? Let's define left I as the last occurrence of AI before I. How do we compute left here? For each number 1 to n, let's store all the indices of their occurrences. Here's an example with the array on screen. The indices of 2 are 0 and 7, the indices of 1 are 1, 2, 5, and 6, and the indices of 3 are 3 and 4. Now we can iterate through the occurrences of each value. For example, left 2 would be 1, left 5 would be 2, and left 6 would be 5. Now let's define right I to be the first occurrence of AI after I. How can we compute right? We can do it in a pretty similar way to computing left. Now let's look at the impossible condition again. Can we try to fix some values? Try yourself first. Let's try to fix k and set I to left k. Now look at the array on the screen. Say the fixed k is at index 5, so left 5 would be 2. For I equals 2, what is the first index in which the impossible condition from before is true? For it to be true, there has to be a value in between 2 and 5 and appears after 5. What is the first value where this is true? The value 2 appears in between index 2 and 5 and also appears at index 6. Let's generalize this now. How can we find the smallest index in kn that appears in left k, k? We can use a minimum segment tree. I will not explain how it works, but I will link some tutorials in the description. All we need to know is that we can perform these operations in O log n time. Set ix will set the ith element to x, and get min lr will get the minimum value in the range lr exclusive. Let's set the ith element in the segment tree to right I. We can use the minimum segment tree to query left k to k and find the smallest value. But there's one issue. Get min 0, 3 returns 2, which is less than 3. How can we prevent this from happening? We can do a sweep line approach. We can query each range left to right. Once we get an index, we can delete it from the segment tree. For example, once we get to the second 2, we can remove it from the segment tree. This way we won't have any problems. Let's define killed I as the first index k, such that the subarray ik is bad. Now how do we answer these queries? In the range LR, if there is a killed I that is less than or equal to R, then the subarray is bad. We can maintain a segment tree to find this like we did before. Let's now look at the code for this problem. First, we input everything and calculate left and right like we defined earlier. If there is no left eye, we can set left eye to -1. Then we do the sweep line to calculate killed. Instead of deleting the segment tree, we just set it to an arbitrarily large number to act like deleting it. Finally, we perform the range queries to see if there is any value of k that makes clearing the subarray impossible. If there is, we output no, otherwise we output yes. Thanks for watching, and I hope you found the video helpful. Please like, subscribe, and comment if you did. Thank you.